I'm very happy to welcome Linda here to give us a talk on Luzin's N and randomness reflection.
Thank you, Joe.
Thanks for coming.
Thank you for having me. So this is joint work with Arno and Leon. So this talk is about a classical property defined by Luzin, known as Luzin's N. And you can define it for any function. I probably should have written continuous here because that's the only kind of functions I'll consider. I'll actually only consider computable functions throughout the talk, even if I forget to say so sometimes. All right, so computable function or continuous function or whatever has Luzin's N property if it maps measure zero sets to measure zero sets. So pretty much like most functions that you would just naturally think of have this property. So it's more useful to give a non-example of this than to give an example, really. And so my non-example will be the Cantor staircase, right? So this is a continuous function, although it doesn't look like it as much as it's drawn because it's a bit difficult to draw. But of course, this is the function where in the middle third, middle third that you first remove from the Cantor set, you give the function value 1/2, and then in the next thirds that you remove, you give the function value 1/4 and 3/4 respectively. And then the points that are actually on the Cantor set just get whatever value that the continuity of this function demands. So we know that this Cantor staircase function doesn't have n because it's a continuous function, so its range is everything. But if you look at the complement of the Cantor set, its range is only countable because it's all of these dyadic rational plateaus. So that means that the Cantor set itself, which has measure zero, is mapped to almost everything in the range. So there's an example of a function that does not have it. So just a little bit of background and context for this property. So it's related to both measurability and integration. So it sort of makes functions behave nicely for both properties. So F has Luzin's N if and only if F maps measurable sets to measurable sets. That uses choice, of course. Then for the relation with integration, if you assume, for example, that the function has bounded variation, then this property N turns out to be exactly what you need in order for the function to be absolutely continuous, which for, we're not going to use it later, but for our purposes, could be defined as almost everywhere differentiable. And if you integrate and then if you differentiate and then integrate again, then you get the same function back. So clearly, if a function failed to have Luzin's N, then it couldn't really have any nice properties with respect to differentiating and then integrating again, because if you're mapping a set of measure zero to positive measure, there's no way that you could obtain that behavior by integration, because whatever is happening on that measure zero set, if I were integrating something, I shouldn't be able to, to accumulate by doing that. So these functions that fail and you can't obtain them by integrating, and at least with bounded variation, you have this sort of nice characterization. Another important fact that, so we're not going to use this stuff though. This is just sort of for context, why people thought about this N in the past. So another fact, yes.
Is the last one equivalent to N?
The last one equivalent to N. You mean this last one?
Yeah. Is that another way to, okay.
Well, because, so the original definition of N, it's like any set whatsoever.
Mm-hmm.
So if you have a measure zero set, of course, you can always pick one like boldface pi 0, 2. But then this last one, Luzin showed that if F fails N, you can actually always find a perfect witness to the failure. But of course, if there's a perfect witness to a failure, then there's your witness. All right, so I asked an analyst, I told an analyst that I was looking at Luzin's N, and he was sort of surprised. Oh, people don't really study that anymore. And on the basis of this last equivalence, which we can analyze the descriptive complexity of, we can sort of start to get an idea of why people might not very much spend time with this property. because looking from the descriptive complexity perspective at that last characterization of Luzin, we can see that a function has Luzin's n if for every closed set, that set having measure 0 implies that the image of that set has measure 0. So the difficult thing about dealing with the looking about anything about the image of a function is that you run into sigma 1 sets immediately, almost no matter how complicated your starting set is. But the one exception, if you started at the very bottom with a closed set, then because of the fact that the function is continuous, you are still going to have a closed set in the image and be able to nicely calculate what that closed set is. And so for the case of closed sets, this condition becomes arithmetic, and you're just having a single pi11 quantifier over the closed, over the possible closed sets where the witness might reside. All right, so in other words, having n is a pi11 property. And it turns out that it's actually a pi11 complete property, as was shown in the 90s. And I will say a little bit more about this proof later, I hope time permitting. But that could be seen perhaps as a reason why this property is not so much studied. It's a little bit hard to work with. However, where an ordinary mathematician sees a pathology, a recursion theorist sees an opportunity. So, hooray, it's a really complicated property. And maybe this property should have some pointwise characterization in terms of higher randomness. So how do we see this? So I put this question mark here because what's written here is not really rigorous. It's just like, here is a kind of theorem that we might hope should happen. So Luzin's n, here's just the definition, again, of Luzin's n. If we try to think about this definition, though, from the pointwise perspective, kind of what it's saying is, if I have an element of a set of measure 0, so have a non-random element, then when I map it over to the other side, it's still in a set of measure 0, so it's sort of caught by some other test. So it's still non-random after you apply the f. Or considering contrapositively, Luzin's n is some kind of randomness, so-called randomness reflection. If f of x is random, then x is random. It's kind of in a fuzzy way what Luzin's n is saying. So then the question is, can we make this precise? So what precise thing should be filled in for random in order to make this vague thing a true statement? And then another kind of question that we can ask about the similar situation, of course, has to do with basis theorems. So suppose that we do have a computable function that fails to have Luzin's n. Well, how simple can we find the witness? And we've already seen there are a couple kinds of witness that we might hope to find. We might hope to find a closed witness, or we might hope to find a, just like a G delta witness. Sorry about that. Okay, so we'll look at both of those in a moment. All right, so our plan for the talk is to talk first about the randomness reflection theorems, which was that first question, then about the basis theorems, which is the second question. And then as time permits, we'll finish up with a sketch of, well, you're getting kind of a preview here of what one of the randomness notions that's going to work will be. We'll look at that if we have time. Okay, so just to remind you some definitions of higher randomness. So a real is called delta 1, 1 random if that real is not captured in any null delta 1, 1 set. And it's pi 1, 1 random if it's not captured by any null pi 1, 1 set. And it's Kurtz random if it's not in any null pi 0, 1 set. And all of these notions can be relativized to a real R. And well, we didn't need to do any relativization for pi 1, 1. Just to remind you then, O, Kleene O denotes the canonical pi 1, 1 complete set. And a fact about the higher randomness notions that we will need is that if a real is random enough, where random enough could be pi 1, 1 random, or delta 1, 1 R random for any R that is, this could be hype greater than O. I wrote trying for some reason, but if Y is random enough like that, then Y will not be able to hype compute O. All right, so here is our first set of characterizations of Luzin's N. And so first, I would like to formally define the randomness reflection notion. So let R be any randomness notion, and this could be the higher randomness notions, but any, you can make this definition for any. We'll say that a function reflects R randomness for that notion R, if for every x, f of x being R random implies that x is R random as well. With that definition, then we can show that for computable functions, Luzin's N is equivalent to any of the following things. Kurt's randomness relativized, reflection of Kurt's randomness relative to O, reflection of delta 1, 1 randomness relative to O, a reflection of pi 1, 1 randomness, and reflection of delta 1 randomness plus the additional property that for almost every y from the range, the set of things that maps to y is countable. So this last one seems, like one of these is different from the others. And we would love to remove that, but it's an open question right now, whether that can be removed. So we don't know if reflecting delta 1, 1 randomness, does that mean that you already imply this countability condition? Or is that condition really needed to be included in this list? All right, so lots and lots of kinds of randomness reflection that are equivalent to N. Here this is just exactly copied the definition. So one thing that's important to notice, if we change the notion of randomness, then we are actually changing not only the hypothesis of reflects R randomness, but also the conclusion. So they would both get stronger, both get weaker. So that means that there's no obvious implications between the randomness reflection for the different randomness reflection notions, right? So just because it's Luzin's N is equivalent to pi 1, 1 randomness reflection, that doesn't tell you anything about Martin-Lorf randomness reflection, for example. So that means that we can also show some notions of randomness that do not work to characterize N. And some ones that do not work are Martin-Lorf randomness, weak 2 randomness, or 2 randomness. However, the methods that we use for this, which I'll show you in just a sec, do not extend to weak 3 randomness. So at that point is again a question of whether Luzin's N could be characterized in that way. I guess it's a little bit treacherous to express opinions in recorded talks, but I guess I would be surprised if Luzin's N were equivalent to that. All right, so let's talk about how this theorem is proved. But I'm just going to show one special case, like how to show that a computable function can reflect Martin-Lorf randomness while failing N. See, this theorem is saying that you can reflect this randomness and this randomness and this randomness all while failing N, but I'll just show you Martin-Lorf. Okay, so what it means to reflect Martin-Lorf randomness. Well, it means that every non-Martin-Lorf random has to be mapped to non-Martin-Lorf random. So we'll achieve this by saying first, so we're going to try to build a function, and in order to make it fail N, if you think about it, in order for a function to map for a continuous function to map a set of measure 0 to a set of positive measure, it has to have a lot of very steep slopes in it. So what we're going to do is basically make a function that has a lot of very steep slopes in it, but we're also going to be watching out for the first component of a universal Martin-Lorf test. And whenever such a component presents itself, then we'll stop making steep slopes there. We'll say, okay, the opponent came and said, no, these are the points that are supposed to stay random when you map them. These aren't supposed to be the points that get mapped to some set of positive measure. All right, so we're going to make f really wiggly outside of the first component of a universal Martin-Lorf test, and on the inside of that test, we'll make it piecewise linear. Right, so here on the bottom to illustrate the process. Right, so the initial iteration of the function might just be a line. And after you've declared that the function starts out that way, then the opponent comes in with this u and adds something there. And then everywhere that the opponent has not added something yet, you increase the slopes of the function. So in this case, I'm actually making a lot of n shapes, like n, n, n. That's a kind of a pun, but it doesn't matter. So you make 3 times the, you make each element of the range sort of have 3 representatives in the domain. And then the opponent comes along and says, okay, well, now I'm gonna add this part to the domain. You say, okay, I won't change in there anymore, but everywhere else, again, now with whatever freedom that I still have to change the values of the function, because I'm trying to build a continuous function at the end, of course, with whatever freedom I still have, I just make a bunch of wiggling, like on the wiggling that I already did. Okay, so the tension that kind of exists here is that if you are the function builder, right? So if you are us, then you're trying to make a set of small measure that has really steep slopes. So you're basically trying to preserve some part of the range so that you can always keep making things steeper and steeper and steeper in that part of the range. And the opponent is trying to prevent you from doing that. So the opponent, in order to try to prevent you, will try to basically remove your access to certain parts of the range so you're no longer able to wiggle around it and make the slopes steeper. So the way that this construction works is you arrange things so that every point on the range that you're going to try to keep wiggling around is really redundantly represented. So you can see, for example, right here, if the opponent wanted to remove my access to this part of the range, then the opponent would have to not remove just one of these segments, the domain for one of these segments. It would actually have to remove the domain for all of these segments in order to get rid of this part of the range. So in general, you just maintain that you make it so that the opponent always has to pay the same amount in the domain as the opponent wants to remove your access to in the range. So that's kind of what this part says. And then because U is the initial component of a Martin-Liff test, there's always going to be at least 1/2 of the measure of the domain left. So you're always going to still have at least 1/2 of the measure of the range to wiggle on. Now, this seems to not quite give you what you need, because remember, all right, so there's 2 things that we need to do, right? One of them has clearly been achieved. The other one, there's going to be a problem. So the thing that has clearly been achieved by this is that everybody that's not Martin-Liff random, after we apply the function, it's still not Martin-Liff random. And the reason that this one has been achieved is because whenever a component of the universal Martin-Liff test comes along, we just stop doing anything inside that component. So it's just a linear function with a rational slope there. So if I started out with something that was not Martin-Liff random, and then I apply like a piecewise linear function that has a rational slope to that thing, it's not going to change any of its computability theoretic properties. So it will remain non-random after being acted on by this piecewise linear map. So this part is good. We've achieved that if X is not Martin-Liff random, then the image will not be Martin-Liff random. We need to explain now why such a function would fail Luzin's n. Because basically what's been done here is we just wiggle, wiggle, wiggle like crazy on the outside of the universal Martin-Liff test. Well, that domain where we wiggled like crazy on it, it has a positive measure. And yeah, its range is this large amount of range that I've happened to preserve the ability to wiggle on. But so what? A set of positive measure got mapped to a set of positive measure. Like that's the usual situation. So you do have to do something in order to whittle down the this like set of original just sort of crazy set of positive measure that you start with into find like a measure 0 subset of it that still maps to everything. But you can do that, although I won't say the details right now. Okay, so that's that one, and it's just a hand waving on how the proof goes. I don't like there's details. And then there's details as well if you want to not just do the Martin-Lorf random part, but if you want to amp it up to do Martin-Lorf random relative to zero jump is sort of the furthest that this argument can go. Okay, so far we've just been talking about characterizations of Luzin's N for continuous functions, with that being the only assumption. But for functions of bounded variation, Luzin's N actually becomes quite a simpler property. So when I started the talk, I said we weren't going to use that absolute continuity thing. We still won't use it. But the interesting thing about Luzin's N for functions of bounded variation is that in the presence of the assumption that the function has bounded variation, Luzin's N actually becomes much simpler. It becomes pi 0 to 3. So that means that when you restrict to that, then you actually can show that Luzin's N becomes equivalent to randomness reflection for certain lower randomness notions that you wouldn't expect without this bounded variation assumption. So we can also show that with bounded variation, Luzin's N is equivalent to reflection of Kurt's randomness relative to zero jump and equivalent to weak 2 randomness. And then finally, if we we could wonder if we could even like weaken these further, like just to Kurt's randomness or just to Martin-Lorf randomness or something like that. And it turns out that this question has actually been studied by Bjørnvig and Merkle. They were looking at relative absolute continuity of measures. But it turns out that if you're looking at two measures and you look at the like sort of the cumulative distribution function of one measure relative to another one, then that whether or not that function has Luzin's N turns out to be related to whether or not the one measure is absolutely continuous with respect to the other measure. So they were studying measures, but they essentially showed that neither Martin-Lorf randomness reflection nor Kurt's randomness reflection would be enough to apply Luzin's N, even if the functions are strictly increasing. So not even just bounded variation. All right, so that's sort of the first part and bird's eye view of all of the randomness reflection results. Any questions so far?
Yeah, Linda. So the theorem, the last theorem on the previous slide. So that's like that supersedes the sketch you gave, right? Except that the sketch you gave can be modified to prove something stronger than what you said. Did I understand something correctly?
Yes, I see what you're asking. So the important part about this theorem is the even for strictly increasing functions. So the sketch that I did here, when you do all this wiggling, the function becomes extremely not of bounded variation. So we know that the property of Luzin's N itself becomes a lot simpler in the presence of bounded variation. So then we said, okay, let's tie our hands from this method. This is sort of inherently an unbounded variation method. Then what can we show? And what Bjørnvig and Merkle showed is that even if the function is increasing, then this does not work to characterize it.
Okay. Thanks.
But like, so in this one for bounded variation, for example, here weak 2 randomness does characterize. But the argument that I showed on the previous page says that weak 2 randomness would not work in the general case, but in the bounded variation case, it does work. Oh, actually, I see what you're saying. You may be right about this last one.
Sorry?
You may be right about this last one. I'd have to think about that.
Okay.
Okay, so basis theorems. So in order to talk about basis theorems, it's relevant to consider this pi11 completeness result that that I'm basically going to give a proof sketch of, which is literally a sketch. So we want to show that the set of continuous real valued functions with Luzin's n is pi on 1 complete. So we're starting out with basically some tree, and we want to know whether the tree is well-founded or not. And if it's well-founded, then we want to make a function that has Luzin's n. And if it's ill-founded, then we want to make a function that does not have Luzin's n. And in order to do this, the starting point is a fat Cantor set and a function which gives the cumulative, kind of the cumulative distribution function for that fat Cantor set. So it's a function which is similar to the Cantor staircase, but it's different in an important way. So it's similar because due to the fact that D has a fat Cantor set, its complement is dense. And so this phi has lots and lots of sort of flat places everywhere. But it's also different because since D is a fat Cantor set, the set of points where this function actually sort of increases, that set has positive measure. So this building block function phi, it has Luzin's n. All right, so here's my phi. So now what they do in order to get this result is they say, all right, every element, every node of the tree is going to correspond to a widget that is sort of finitely many copies of phi. So because I have this root node of my tree, then I add this starting copy of phi. And then suppose I notice that the tree has a child. And maybe it's very, very late. I need to make this function computable, so I can only like change it by a very small height. But whatever height I can change it by, I pick a whole bunch of locations. Right? So maybe I'll pick this location and this location and this location and this location, so that by wiggling with no more than the height that I am permitted, I can still, if I go like up and down or down and up like that, and like that, and like that, I pick enough of these close enough together that I'm still sort of redundantly covering the entire range by adding these extra wiggles. And then on each one of the upslopes of one of these wiggles, instead of having just like a straight upslope, right? Instead, it's going to be another copy of this phi, but small. Right, so now all those like little flat places are back. So to this one node, there's associated a whole collection of these widgets. And then if this node ever has a child, you recurse that inside each one of the widgets that was associated to this one. Okay, so this is kind of what the construction looks like. And I'm sort of waving my hands in super vague way, but the thing to kind of notice about it is that because of the fact that phi has Luzin's n, if this tree happens to be well-founded, then you're doing all this complicated stuff, but at the end of the day, everything peters out. At the end of the day, you just have a union of these countably many places on which this function phi has Luzin's n, and then a whole bunch of places that essentially correspond to leaves. On the other hand, if there is actually a path through this tree, then by following the locations where you act for the nodes that are on that particular path, you end up with a decreasing intersection of closed sets that ultimately its image will be everything, but it will get down to measure 0. Okay, so that's like a super sketchy version of what this proof is kind of like. Okay, so let's look at first the case of basis theorems for closed witnesses. So we know that if a continuous function f fails n, then there is going to be a closed set to witness that failure. So that pretty much immediately tells us that you can always use Kleene O in order to find such a witness. And you can even find one that's hyperarithmetically low. And reason is because, once again, if you're just considering closed sets, then observing, oh, here is an example of a closed set which has measure 0 but maps to something whose measure is non-zero, that's an arithmetic observation. So that means that if a function fails Luzin's n, then the collection of closed witnesses to that failure is sigma 1, 1, and you can just use the Gandy basis theorem in order to find some particular example of a closed set. And the result that we just sketched actually shows you that you can't do that much better than that if you're trying to look for closed witnesses. Because, for example, if you tried to improve it to say, well, could you always find a delta 1, 1 describable closed witness to the failure of n when it exists? Well, you know that you can't always find one, because if you would, if that were true, if you could always find a delta 1, 1 closed witness to the failure, then you would be able to write Luzin's n in a sigma 1 way, in a sigma 1, 1 way, as is written here. Because you could, using a sigma 1, 1 quantifier, quantify over all of the delta 1, 1 closed possibilities and then just see which one has it. Okay, so if you are looking for specific examples of functions that fail to have Luzin's n, but nevertheless send every null pi11 closed set to a null set, then you can go through that construction that I sketched, the HPZZ construction on the previous slide, and start out with a well-founded tree, or excuse me, start out with an ill-founded tree, but none of whose paths are hyperarithmetic. And then you can come up with an example, a bad example like this. Okay, so that's the situation for closed witnesses. And I ran out of questions to ask about closed witnesses. I don't know if there is a way to try to thread the needle between, delta 1, 1 is not enough, but you can get hyperarithmetically low. All right, then the other kind of basis theorems that we might be interested in are the G delta basis theorems, or topologically. But we'll allow ourselves now to just look for a pi02 witness. So here theorem 2 is coming back. So the reason that this is labeled the same way, if you remember it, the thing that was theorem 2 way back in the day was saying that Luzin's n was not equivalent to Martin-Wolf randomness reflection or weak 2 random reflection, or so the same function that we constructed back then, this function is showing us that there is a computable function. It fails Luzin's n, but it sends the complement of, so it sends the Martin-Wolf non-randoms to a null set. And then I didn't show you, but we were able to amp that construction up to have an oracle in here. All right, so so you can send everything that is not weak 2 random to a null set and still fail n. Then the open question that's related precisely to the open question of whether you can amp that previous construction up to weak 3 random is this: can a computable function fail Luzin's n, but send this is the same thing as saying that send every element of the complement of weak 3 random to a null set. So I don't have anything to say about this basis theorem because it's so open other than the construction that I showed you. But I just wanted to make the remark that this HPZZ construction so far is kind of no help. Because even though it's super hard to find the closed set for which that construction sends to a set of positive measure, it's really easy to find a pi02 set that construction sends to a set of positive measure. Because if you just put the full tree as the input and look at every single possible place in the domain of the output where things could be going hairy, that's already a null set. It just, everything gets very thin very fast, and it's computably so. Oops, sorry. Okay, so that's everything that I have to say about basis theorems. All right, and then the last, or any questions? Okay, and then the last part of the talk is to sketch a little bit the proof of the equivalence that Luzin then has with all these various higher randomness reflection notions. So here's just repeating the theorem from before.
I do have a question about this theorem, if I may. So it implies that having Luzin's n says that f inverse of y is countable for almost every y?
Yes. And that's a classical fact about Luzin's n which is known, which I probably should have put on the first slide.
Yeah, I just wanted to double check because I wasn't, like that's what it says, but I thought the other possibility was that you meant under this extra condition, but you actually mean what you were saying.
Yeah.
Okay, cool.
So in fact, and I'll get into this now, these other conditions, you know, each one of these other ones implies the f inverse y is countable. You just don't have to, so you don't have to write it. It's like already baked in. Okay, so let's talk about this countable fibers business. So there is a theorem of Martin, which says that anytime you have an uncountable delta 1, 1, and y set, if that set has the property that each one of its elements computes y, hyperarithmetically computes y, then some element of that set hyperarithmetically computes O relative to y. And we're going to be usually thinking about this in a situation where A is the inverse image of some element from the domain. So A is just some set of points that all map to the same point. So the corollary that this theorem gives us is exactly that if f reflects enough randomness, namely delta 1, 1 randomness relative to O or pi 1, 1 randomness, if f is reflecting that much randomness, then f inverse y ends up being countable for every sufficiently random y. To see how this is proved using Martin's theorem, we let A be the set of things that map to y under this f. Well, since everything in A is getting mapped to y by a computable function, everything in A is certainly hype computing y. Everything in A is actually just computing y. So suppose that A is uncountable. Then by Martin's theorem, we know that there is some element in there that hype computes O. However, hype computing O, as we saw previously, is not compatible with being any of these high types of randomness. So that means that if f inverse y is uncountable, and if the function actually does reflect these randomnesses, then if y were really random, x would have to be really random. It could not hype compute O. Right, so if f really reflects these higher randomnesses, then for those y's that are really random, f inverse y has to be countable because every x in f inverse y is going to be too random to compute O. All right, so this method of showing that that almost every fiber is countable doesn't work if we just assume reflecting delta 1, 1 randomness, because a delta 1, 1 random is happy to hype compute O sometimes. But we don't have a proof the other way either. All right, and then finally, I will wave my hands about proving the main theorem. So this theorem now looks a little bit different because I threw away the part about quartz randomness, because that has to do with the closed witnesses and its different kinds of arguments. But just considering the delta 1, 1 type witnesses, there are 5 equivalences that we want to look at. So you should think of this equivalence number 3 as essentially saying that f reflects delta 1, 1 O randomness. It turns out that you can you don't really need O here. It can just be any R that can hype compute O. So I've just written it in the more general case for this slide. And then there's a new condition, which is F reflects delta 1, 1 R randomness for all R on a cone. So this new condition, it's more of a proposition. Like it's almost a direct translation back and forth between Luzin's N and between this 2. So if 2 implies 1 is very direct. If F reflects delta 1, 1 R randomness, then that means that every delta 1, 1 R null set has to get mapped to a null set. So in particular, every null set gets mapped to a null set because every null set is delta 1, 1 R for some, is contained in a delta 1, 1 R null set for some R. Right, so that's 2 implies 1. And then to see that 1 implies 2, you just have to use the fact that every null sigma 1, 1 set is contained in a null delta 1, 1 set. So suppose that a function really has Luzin's N. Start out with a delta 1, 1 R null set. You know that its image is null. The question is just, well, is its image still a delta 1, 1 R test? And well, it may not be, but it'll be contained in a delta 1, 1 R test because its image will be sigma 1, 1 R, and that'll be contained in a delta 1, 1 R test. Okay, so one if and only if 2 is just some kind of restatement, and 2 is the one that we'll think about when proving the other equivalences. And the direction from that 2 implies 3, 4, and 5 is a direction that I will not show you, but I will say something about the other direction. So in order to go the other way, so I'm going to assume any one of these 3, 4, and 5 and show that it implies 2. So we prove, I call it a lemma here, it's a theorem in the paper. And it's basically one of these results that says that if you have something that is like super random, and if that thing hype computes something that is pretty random, then the thing that was pretty random is actually also super random. So how super random are we going to assume that Y is? Well, let's say at least delta 1, 1 R random with R hype above O. All right, so then to see that any of these 3, 4, or 5 imply 2, fix some R that is greater than O. That's kind of for cases 4 and 5. If you're in case 3, if you just know that F reflects delta 1 R randomness for some big R, then just pick this R to be bigger than that R as well. All right, so I want to show 2. So given some big enough R, so we're just going to verify it for all R on a cone. So given some R that's like super big, and given a delta 1 R random Y, and something that maps to it, what we need to show is that that something that maps to it, it's also delta 1, 1 R random. Now we're assuming some amount of randomness reflection. The R here is like much more randomness than the amount of randomness reflection we're assuming. We're only assuming like pi 1, 1 or delta 1, 1 or so on reflection. But this Y is also delta 1, 1 random or pi 1, 1 random or so on. So that means because of the randomness reflection, X is at least delta 1, 1 random in all of these cases. So since X is at least delta 1, 1 random, it satisfies that part of the theorem, of the lemma. The other part of the lemma that we need to know is that Y can hype compute X. The reason that we can know that in all 3 of these cases is because, as I discussed previously, in all 3 cases, even though this one is only written, but it's implied in these other cases, F inverse Y is always countable for the Y's that we're considering. So since F inverse Y is countable, then Y does hype compute every element of it. And that gives the second condition, and so you can apply the lemma and conclude that that X is actually super random, and so the randomness reflection works. Oh, and that's the end. Thank you.
Thank you, Linda. Are there any questions that people have been saving?
So, Linda, nice talk. I'm wondering if the analyst you told you were working on this, if you could explain to him any of your results and what he thought of them, or her.
Well, I haven't seen anybody since COVID.
Oh, so this was all okay.
I will tell him after we start seeing each other again.
Yeah, so you think you think you can explain what the results say is what I'm really wondering about? Will that make sense to someone who doesn't know any logic?
I think so. I mean, the starting point of the pointwise randomness stuff, which is just, well, how, what kind of sets do you have to avoid in order to start doing the typical behavior? Like, I'd be willing to give it a try anyway.
Okay. I hope so. I hope it works.
I hope so.
Don't analysts know what pi11 sets are?
Pi11 relative to R.
Hmm.
Random,
Okay.
Pi11 and R random. Well, that's what I was wondering if they know. They know what, mostly they know what Pi11 sets are.
Right. Are there other questions or comments? Okay, well, let's thank Linda again.
I have a question.
Oh, sorry. Let's
Sorry.
thank Linda, but in a moment.
I want to channel Andre and ask is there any sense of asking about reflection between two classes of randomness that are not the same?
You could absolutely ask those questions. And so many of the results that, let's see. Well, I'll just say you can definitely ask those questions. We didn't undertake a detailed study of that graph. Somebody could.
All right. Well, let's thank Linda again in our whatever way we choose. I'm going to clap.